Okay, let's dive into this. We're going to take a look at a scientific paper from March 2026 all about marine diesel engines. But here's the thing, this is no ordinary paper. It's, well, it's almost completely empty. And that is where our story really begins. So here it is. You've got a title, you've got an author, a publication date, all the usual stuff. But then you look closer. The abstract section, totally blank. You scroll down, there are zero citations, zero references. It's like a ghost, right? A placeholder for research that, for all we know, doesn't even exist. So, what do you do with that? And that's the real question, isn't it? I mean, it feels like a total dead end. But what if it's not? What if it's actually an invitation? We're going to treat this whole thing like a detective story, using the faintest clues we can find to piece together a much, much bigger picture of how engineering really works. Now, the page isn't completely blank. See, the research platform it's on has automatically linked a few recommended publications. These are our breadcrumbs, our only leads in this whole thing. So you know what we're going to do? We're going to follow the trail. And what a trail it is. Our clues span more than a decade of research. We've got a 2008 study digging into the physical stress on these massive engines. Then in 2009, a paper looking at how lubricants were evolving. And fast forward to 2019, a huge breakthrough in how that lubricant gets delivered. Right away, this timeline tells you something. The problems these engines face are persistent, and the hunt for solutions never, ever stops. Let's start with that 2009 paper and our first big theme, lubrication. You can think of it like this. If fuel is the food for these giant engines, then the oil is their lifeblood. And as these engines got more and more powerful, that lifeblood had to get a whole lot stronger. This quote from the paper just sets the stage perfectly. You know, back in the late 90s and early 2000s, there was this massive push for engines that were way more powerful and way more efficient. But here's the catch. More power means more heat and more pressure. The oils they were using before, suddenly they were being pushed to their absolute breaking point. So the 2009 paper actually compares the oils of its time to the ones from about a decade earlier, and you can see this huge leap in technology. We're talking a nearly 20 degrees Celsius jump in heat resistance, higher detergency, that's basically the oil's ability to keep the engine clean from gunk, and better oxidation stability, which just means the oil doesn't break down as fast under all that stress. It was a massive, massive step forward. But here's the thing, improving the oil itself, that was only half the battle. The next big idea completely shifted focus from chemistry over to mechanics. It stopped being just about what the oil was made of and started being about how it was being delivered. The new question was, how do we get the perfect amount of oil to the exact right spot at the exact right time? And the 2019 paper gives us the answer. This new electronic system was a total game changer. It gets rid of the old clunky mechanical pumps. Instead, it can inject oil with the precision of a tenth of a millisecond. It targets the piston rings directly, which is where it's needed most. And get this, it's smart. It actually adjusts how much oil it's using based on what the engine is doing at any given moment. So what's the payoff for all that precision and intelligence? This number, a reduction in cylinder oil consumption of about 25%. In an industry where fuel and oil are two of your biggest costs, saving 25% is absolutely enormous.
Okay, so we've cracked one part of the puzzle, lubrication. But remember our other clue, that paper from 2008? It points to a totally different challenge. This one isn't about the fluids, it's about the solid metal parts of the engine and the unbelievable physical stress they have to endure day in and day out.
Now, to really get this, we need to know what a cylinder liner is. Super simple, I promise. Just think of it as the giant metal tube that contains the massive explosion that drives the piston. It is the very heart of the engine's power, and man, it takes a beating. So the core finding of this 2008 paper was just fascinating. The engineers had these super powerful computer models to calculate how the cylinder liner should bend and deform under all that heat and pressure. But when they went to actually measure it on a real, running engine, the numbers didn't match. So why the gap? Well, the researchers found that their models, as advanced as they were, just couldn't capture the full complexity of the real world. The shapes were more intricate, the temperature readings weren't quite perfect, and the way all these different metal parts touch and press against each other was just incredibly hard to simulate. It's a perfect example of that constant battle in engineering to make the theory match a messy reality. So we've talked about fancy oils and bent metal, but why does any of this really matter? Let's zoom out for a second and connect these tough engineering puzzles to the world we all live in. Just look at this data from the 2019 paper on that electronic lubrication system. This isn't just a lab experiment. It's been retrofitted onto over 120 massive ship engines out there in the real world. And the payback period, that's the time it takes for the savings on oil to pay for the upgrade, is less than 2 years. That is an incredible return on investment.
And this is the big takeaway. These aren't just any old engines. They power the container ships that are the absolute backbone of our global economy. That 25% reduction in oil use, when you multiply it across thousands of ships sailing 24/7, has a staggering impact, not just on costs, but on the environment too.
So let's bring it all back home, back to our empty paper. We started with literally nothing but a title. And just by following a few faint clues, we've managed to uncover this deep, fascinating story about how innovation really happens. The lubrication clues, they told a story about a relentless push for more efficiency. The deformation study, it showed us the constant struggle to make our models match the real world. And the empty paper itself, it taught us that research isn't just a single document you publish and you're done. No, it's a continuous, ongoing conversation built on decades of work. That 2026 paper isn't empty. It's just waiting for the next chapter to be written.
And that really leaves us with one final thought. We managed to piece this whole story together from just a few papers scattered across a single decade. It just makes you wonder, with technology moving faster than ever, what incredible breakthroughs will the next blank page inspire? What mysteries are out there just waiting to be solved?